The purpose of this video is to provide a slightly more in-depth understanding and investigation into the fourth tab in Complexit on visualizing and exploring your cluster solutions. If you recall, we already have a video on how to run the artificial neural net, the self-organizing map, and also a basic video that talks about this fourth tab. But there are a lot more nuances that need to be explored, and so that's what we want to do in this particular video. Again, we're looking at the relationship between the K-means solution, which you run in tab 2, and that you have to decide ahead of time based on theory or whatever, how you want to cluster things in comparison to the unsupervised solution that was found by the SOM. So one of the first things we need to talk about is are these statistics here. What exactly do they mean? We talked in the previous video that topographical error and quantization error are ways of measuring the goodness of fit of the SOM. If we look at the actual definition, quantization error technically is calculating the mean squared Euclidean distance, Euclidean being the shortest distance between 2 points is a straight line, between the sample vectors and their respective cluster prototypes. And then in turn, topographical error is just basically saying you picked a particular cluster for the case to land on. How good is that fit? So when you look at Complexit, for example, in the grid, here's the 5x5 grid, right, that comes out of the solution, because that's the 5x5 grid we've chosen. And again, in the next video, we'll play around with shrinking this or expanding it. But each of these quadrants, therefore, represents a cluster. So cluster 1 all the way up to cluster 25. So quantization error and topographical error are telling you how the goodness of fit is for this particular solution. For those interested in a more in-depth analysis of that, you can go to the tab 3 and go to the CRAN website, which provides some PDFs and other more in-depth explorations that help you better understand these statistics. But for now, it's sufficient to know that they're pushing themselves towards 0, and that's demonstrating a good fit. If you read through, it's basically just saying that we did run the SOM, that the grid is 5x5, and we're using neighborhood estimate, which is how do we place things around a particular quadrant, right, here, based on what's a Gaussian distribution, which is a basic bell-shaped curve where you hope the majority of cases are in the middle and the margins are less cases. This Euclidean final energy is another somewhat sophisticated concept, but ostensibly what it is as the algorithm is running across time, say here go from 0 to 2,000 iterations, the energy level or the degree to which the fit is getting better and better is to decrease across time. And so again, it's just another measure that's provided to demonstrate the overall final fit. Again, for those more sophisticated in those statistics, perhaps writing up a research paper, it's good to look at the CRAN package to explore a little bit more about what that means. Then we have an analysis of variance and the degrees of freedom relative to computing the F statistic. And then we have our variables. Here, for example, is income in 2014, which is a measure of deprivation. So the higher this score, the worse off. And then same with employment and other key factors, which we'll review in a second. But what you're getting here is something slightly different from what you get on the visualization. If we recall, for example, if you go to the go to the color box and you look at income 2014, you're seeing how income is distributed, or I should say disparities in income are distributed on this grid relative to the cluster solutions in the cases. So you see, as we recall, the deeper the color, the more intense the issue is. And when we look at the clusters and cases that are put in here, these are the cases and clusters that are the worst off. And we can see that in the bar plot that they have the highest levels of deprivation compared to the cases down here, which have the lowest level. And that's what's nice about the SOM map is it places things relative to each other in terms of not just what cases fit there, but how those cases and clusters compared to the others. So we can assume that this case in clustering over here is the most unlike this. And so you should see nice distributions similar to this that show that. That is, however, different than what you're getting here. What this is telling you over here is how important those factors were in making up the actual clustering of the cases. In other words, which factors accounted for the greatest. And again, that is typical to what an F statistic is. So you see income deprivation was 12, employment 20, birth weight 10, death rate 28. So you can see that death rate, income, for example, played a huge part in determining where cases were placed. The larger the F value, the more significance that factor played. And then you see that they're also significant at P equals all the way out this way with 3 asterisks at the end. So these are nice statistics, and they are all put at the end of the report, along with a number of the visualizations that you get here are downloaded and ready for you in the report tab. In terms of thinking about this, again, what we want to do is really take a look at the SOM solution relative to the K-means solution and get a feel for, do we have the type of distribution that makes sense for the data that we've examined? So you see in this map, for example, all clusters 1 are down in this area for the most part. We have 1 over here. In comparison, the 3s are all over here, 2s are distributed somewhat, and your 4s are up here. So the question then becomes, what might be making those distinctions? If we go to the bar plots, one of the things that we see is that certainly there is income deprivation across these, right, and education deprivation. You see death rates are also high. Remember to read this as this is variable 1, 2, 3, 4, 5, 6, 7, which when we were doing the actual analysis, 1, 2, 3, 4, 5, 6, 7, those are our 7 variables. One of the things that stands out, though, is you notice that this cluster down here, crime and violence, seem to be a significant issue. You see a little bit less here, and then more down here and sort of down here. So it seems that there might be something standing out over here that distinguishes these groups that might be struggling a bit with deprivation compared to these groups that are dealing with deprivation across economic and educational lines. All of these groups over here have low crime and violence rates, as well as doing well on economic and educational factors. So that's a type of distinction that then makes you think, well, maybe we might want to explore that a little bit more. So one of the things you can do then is go in and perhaps push your cluster analysis. Let's try, for example, a 5-cluster solution. We see that the F statistic goes up quite significant in comparison to the 4-cluster solution. 4-cluster solution's at 69, whereas a 5-cluster solution is getting us a nicer fit overall. And we're getting cases that are much closer towards 1. When we then go and rerun the SOM, we can compare those results, and we see that the distinctions here now in terms of crime and violence stand out a little bit better. So a distinction's been made. These communities over here as compared to these over here have educational and economic deprivation issues. These do as well. These would be sort of moderate, severe. But then this crime thing is sticking out, which makes you think perhaps maybe you might want to push the SOM a bit to see if that provides a slightly more sophisticated picture. You notice the quadrants change now to 36 because this is a 6x6 grid. And so we again have the communities that we would expect who are doing quite well and around. And then you see the deprivation communities over here separated. But now we have a real separation here from these communities versus these where crime is a major issue. And when we look at the actual distribution now, we see that amongst the cases that are in cluster 2, we're getting a nice distinction amongst them based on this factor of violence and crime, as compared to the 5s, which are up here, and the 1s over here, which are health communities, and then all the 4s are placed down here relative to the rest. So actually this 6x6 grid is starting to give us a more sophisticated view. And again, looking at the color distribution of key factors, we see that this plays an important role. If we go down to the violence, for example, we see that violence is definitely an issue over here, but really significant up in these quadrants as compared to the rest. Same with theft and crime. We see this particular cluster having the greatest and then set up. And again, that makes sense when we compare it to the names and distributions, that this particular cluster right here and the case associated with it has this as the most significant issues compared to others. So this is one of the real strengths of this technique, is you can move back and forth and do that kind of analysis. And then prototypes, which is fancy for the factors. Again, if you just want to see that spread out in a higher degree of relief, you can then see how these factors are distributed. Again, you see these crime and violence factors being important over here, playing a lesser degree as you go down. And so we're seeing consistency across the analyses. The other nice thing is this gives you distance between prototypes, so it's showing you that the cluster and cases up in this area do differ significantly from what's down here. And we can also see that in what are called the U-matrix distances. This you could almost think of as a hill or valley, depending upon how you want to view it, and these sitting up on the opposite sides of that in terms of how these cases are distributed. There is significant distance between the cases on either end of this matrix. So again, it's giving us a much more sophisticated way of looking into the data and being able to make sense of how things go together. So just in summary, you have your observations, which you can look at in terms of the distribution of any particular variable. You can look at the bar plots to see the actual profiles. You can look at the names to see the K-means solution in the particular cases. And you can then do box plots to see how the cases within that particular cluster fit. You're also able to go back and try different cluster solutions to see how those fit, perhaps push it up to 6 maybe even, and see how that fits. That's an even better F statistic. How does that then compare when you actually go out and run a 6x6 SOM to get your analysis, and then to compare your overall solution again? And you can see that as you start to do that, you get a more refined view of the data. That doesn't mean you always want to do that. Sometimes you might just want to get the most basic insight into the data. And so you might run a very small SOM to just get a crude and rude sense of things very quickly. And again, you can see in the smaller solution, those distinctions amongst communities struggling relative to crime and violence as compared to economic and educational factors are sort of lumped in together, whereas in the more sophisticated versions, they're not. So again, the goal here is not necessarily to get a one-to-one relationship between what the K-means has arrived at in comparison to the SOM, but to use the two together to get at your best intuition about the data.